Welcome again to my science tutorial, and in this video we're going to be looking at electrophilic aromatic substitution reaction as part of our series of teaching on aromatic compounds, aromaticity. So in our introductory videos we did mention that aromatic compounds are really stable, really stable, and so they don't really undergo the reactions that a normal alkene will undergo. So we know that alkenes undergo what is known as electrophilic addition reaction. Electrophilic addition reaction. But when it comes to aromatic compounds, they undergo electrophilic aromatic substitution reaction, which is usually referred to as EAS. So this it is abbreviated as EAS for short. Alright, so what this video is to do is to give you an introduction about how this is done and what it is about. So really simple, when we talk about EAS reaction, it is a reaction which sees a replacement of a proton on an aromatic ring by an electrophile. So what I'm saying is, if we have an aromatic ring like benzene, so we have benzene here, we have benzene here, we have these hydrogens on it all around. What EAS seeks to do is to set a reaction where we have an electrophile. Remember, it has a positive charge coming in, and what is going to be the product is going to replace one of these protons, the hydrogens on the benzene ring. So we now have benzene again, but this time instead of the proton here, we're going to have an electrophile, another electrophile, replacing it. So basically this is what EAS is about. So like I did said, aromatic compounds are really stable and they don't easily undergo these reactions that alkenes undergo. If they have to, then it requires some special condition, and for that property, aromatics are refers to they have diminished reactivity. Let me put that here. Let me put it here. Diminished reactivity. Diminished reactivity. So it is this property which shows us that aromatic compounds don't just undergo a normal alkene reaction. So if we take an alkene, if we have an alkene, C double bonded to C, and then we bring in something like HCl, so let me put an HCl here, and that's it. What is going to happen is we're going to be having this bond breaking, picking this hydrogen, and all the electrons in this bond is going to be thrown onto chlorine. So we're going to have an intermediate. So we'll have a C, now singly bonded to C again, and then we have this, and then we have this carbon, this time having this hydrogen, and this carbon will now have a positive charge on it. So we say we have a carbocation intermediate. So carbocation intermediate. Carbocation intermediate. So this is the intermediate. So our chlorine, which is being displaced from here, is now here, very rich in electron. So it has a negative charge, and so it's going to come all this way and attack this carbocation, and so we're now going to have our chlorine added to the carbon. So we have chlorine here, Cl, and then we have a hydrogen here. So if we have a reaction such as this, that is what we call electrophilic addition reaction. But it is not like that with aromatic compounds. They undergo electrophilic substitution, aromatic substitution reaction, aromatic substitution reaction, and these reactions require some special conditions. So we have so many examples of electrophilic aromatic substitution reactions. Let me just give you some of them. So let's say this is our benzene again. If this is our benzene, if this is our benzene, it can undergo a reaction known as sulfonation. So let me just put here one, sorry about that, sulfonation. So this one, when we do that, we're going to have a sulfonyl ion being added to the benzene. So we're going to have a benzene. By this time we'll be having SO3H attached to it, and then we can also have a silation. So let me put a silation here. Silation. What happens if we have a silation? We're going to be having the acyl group being attached to the benzene. So we have the benzene here, but then we have a acyl group attached to it. And then another example is halogenation. We can also have halogenation. We can put it as halogenation. So we can have halogenation, and you know what that is? Adding a halogen to the benzene ring or the aromatic compound. So this, once again, we have our benzene here, and then we have a halogen attached to it. A halogen attached to it, and then we can also have nitration. So let me put it here. We can also have we have NO2 attached to it, and we also have alkylation. Alkylation, which will give us a benzene with an R group attached to it, R for the alkyl group. Alright, so basically these are some examples of nucleophilic aromatic substitution reaction. Oh, see, that's a nucleophilic electrophilic. Alright, but then there are some things we have to take note of. Um, the ions, the electrophile ions, which will be added to the benzene ring or the aromatic compound, we need to know their structures because it will give us an understanding of what the reaction mechanism is going to be like. So for example, if we take sulfonation, we take sulfonation, we have the sulfonyl group, we have S bonded to O, and then we have O minus, and our sulfur positively charged, so that's going to be our electrophile, or you can equally write it as S. O, by this time we have a hydrogen attached to it. So this is going to be our electrophile if we are doing sulfonation. What if we are doing, let's call this number one. If we are doing halogenation, then we know we are talking about halogens. So our electrophile is going to be Cl plus chlorine plus bromine iodine. So the halogens, group 7. And when we are doing nitration, so we have number 3, nitration. What is going to be our electrophile? Our electrophile is going to be NO2 plus. And what is the structure of NO2 plus? We have nitrogen doubly bonded to oxygen, and there is a positive charge on the nitrogen, which makes it to be an electrophile. What about acylation? Okay, this is for acylation. Electrophile is an acyl group for sure. So our electrophile is going to be we have R, which is bonded to carbon, doubly bonded to oxygen with 2 lone pairs. I remember we already have 3 bonds attached to the carbon over here, and oxygen is so electronegative such that it's going to cause a positive charge to be on our carbon, and this gives it our electrophilic property. So that is these are the electrophiles we need to look at for when we're carrying out any of these processes. Of course, if you are doing alkylation, our electrophile, so put here alkylation, our electrophile is simply represented with an R group. It must have a positive charge on it. So guys, this is the introduction to electrophilic aromatic substitution reaction. So in the next video, we're going to be looking at some mechanisms, the step-by-step mechanisms in which these reactions are taking place. So don't forget to subscribe to this channel and share the link with your colleagues. Thank you.